So today we're going to look at the Schneider with a HIPERFACE sine cosine feedback device. How do you get higher sine cos interpolation, more counts per rev, when the absolute counts per rev is only 8192, and we're going to get 262144 interpolated counts per rev. So in terms, one count will be 32 times more incremental. So in terms of the fundamental. If we look at the datasheet for the motor, we see single turn HIPERFACE. If we look at the part number, we can see the one digit is a 6, absolute single turn 16 sine cos per revolution, SEK37. We're getting warm. Single turn SEK, 16 sine cos, 1 revolution. 7 to 12 volts, so we'll use a 9-volt regulator on 50 milliamps without load. The encoder is the load. Anyways, here we go. Here's the encoder that's on the motor from SICK. It's a HIPERFACE, SICK HIPERFACE. Again, 16 sine cos, but 512 number of steps. So that's 9 bits. And let's take a look at a regulator. So Copley outputs 5 volts. This thing needs 9 volts. And here's a 24 or 11 to 32 to produce 9. It does half an amp. So a little tiny regulator. I'll show you the wiring here for the Schneider. Okay, so here's the cable from the motor. It's got a bunch of wires on it, different colors. It's got ref sine out, cosine out plus, cosine out, sine out plus. So they're the differential signals for the sine and cosine. There's data plus and hat data, pretty pink color, and 0 volts to, it says 10 volts here, but 9 volts works because the spec is 7 to 12. And so I use 24 to power the regulator, to power the encoder, common ground. So the shield is connected to the frame ground, and the blue is the common ground by which all the signals, sine and cosine, and data on S and S naught are with respect to ground. And so that just plugs into the Copley drive connector here for the plus drive, 26-pin high-density D-sub male. And then the motor connection, just plug in the motor. So we got a nice Schneider cable here that we used to put a Copley connector on with a regulator in line. So let's take a look at CME in the basic setup. It's a brushless rotary motor. It's got HIPERFACE. It's a 9-bit absolute single turn. It has 16 fundamental sine cosine lines, which turns into 9 times 2 to the 9 is 512 times 16 is 8192 counts per rev. 16 sine cosine fundamental line times 4 quadrature is 64. So I interpolated 128 to get 8192 interpolated sine cosine per rev. We can increase the interpolation to 4096, but it's going to affect the tuning. I'm going to go with the fundamental first. Don't ignore your feedback. There's stop parameters, finish. Let's take a peek at the motor. Here's the motor, 10 poles, some inertia, peak and continuous torque, theoretical top speed. 480 volt motor is going to go half speed at 240. Newton meters per amp in newtons per amp RMS, and then per amps peak, the same value for volts per kRPM. Yeah, 88 volts per kRPM. Resistance is 4 ohms, inductance is 20 millihenries. Calculate to get the initial tuning parameters, and we can see we get some current loop bandwidth here. I haven't tuned the current loop yet, but we'd like about 1 kilohertz. 1.2, that's perfect. So I'll use the calculated values. Somebody's been playing with the numbers here. So we'll put in 6,000 for the speed limit. It's warning us you can't do that. But if I had a higher voltage, perhaps I could get 3,000. Still warning us I got 120, not 240. Anyways, these are the gains with the low shift for the high resolution. Let me just open up the file. Okay, so I'm going to restore the file I configured for the Schneider. All right, here's the fundamental. Just going to double check that. Yeah. Still. Okay. Okay. Anyways, let's take a look at the velocity loop tuning. The current loop tuning is fine and dandy. We got a good 1.2 kilohertz. I'm just going to knock this. Ooh, I'm going to calculate values again. Calculate. Okay. That's better. So yeah, that's better. So let's save this to Flash and let's save this to a file. And this will be the 8192 count per rev file. And take a look at the current loop tuning again. That's fine. Velocity is going to go bang bang. The acceleration is still a little bit high. Well, not very stiff, so someone needs to tune this up. The point is, after you do the tuning with 8192 counts per rev, if you just change the interpolation, you have to be careful. You have to cut the gains down. So let's take a look at the paper on this. It's a Schneider SEK17 single turn absolute hyperphase, 512 steps or 9-bit absolute on the 16 poles per rev. So 2 to the 19 times 16 is 8192 absolute counts per rev. Why didn't somebody just say that? 16 line sine cosine times 4 is 64 fundamental times interpolation of 128. Is 8192 counts per rev plus or minus a count. We're going to increase the interpolation. The max Copley is 4096 times the 64 counts per rev post quadrature to give us 626144 interpolated incremental counts. And it's going to be, it's signal to noise ratio. So we're cranking up the gain on some sine cosine. So there's 5 bits of noise. But we do get 626144 resolution, which is 32 times more than we previously had for the fundamental counts per rev. So you will get your absolute position of 6261442, but I'm sorry, 144. But it'll be in terms of 32 divisions of that. So in 8192 is the fundamental, so times 32, like in steps, okay? Anyways, the gain, if you had it set, for example, if you had VP of 200 and VI of 5, which if you take a look here, we can do that. 200, I'm unchecking the low gain shift. Let's say I tune this way. Let's just take a quick peek at that tuning again. Oh, that's well tuned. Okay, let me just save that as the 8192 count file. Geez, Dean, can't you go any faster than this? This makes it for a very boring video. Okay, so again, the values for VP and VI will have to be divided by 32. And we get gains when I increase the resolution. I get 6.25 and 0.015. In order to get back to some real numbers here, 6.25 and 6. I can't do 6.25, just 6, and I can't do 0.15. So let me low gain shift it and look at the note. So multiply these numbers by 256 for left shift low gain 1638. So put in the gains of 38. You see how that came back to 0? So 16. So I'm just dividing the gains and I'm shifting. So there's two operations going on at the same time here. So sorry to make it confusing. And we'll save to flash. And we'll then, after we lower the gains, we'll increase the interpolation. I'll put the max 626144. So now I get more counts per rev. But in terms of absolute, it's still 8192. It's just that it's in 32 times steps. Let's double check the phasing here. Anytime you mess with the feedback, you better check your phasing. It's a little bit funny here. So let's go 120. Okay, that looks pretty good. Say okay. Now I'm going to just reset the drive to get my absolute position on power up. Yeah, so 32 times the quarter rev would be about 65536. So in terms of, you know, incremental counts per rev, but it's still single turn 8192. So there's steps in there for the absolute position, but the count is accurate. Now let's take a look at the tuning with the higher gain. So the current loop, again, does not change. The velocity does, position loop does not. There's some peculiarities here. Yeah, so let's go back and recalculate now with the higher counts per rev. Geez, Dan, you're making up the procedure as you go here. Yeah, so these look pretty good. And I'm just putting in the calculated values from the previous tuning with low gain shift. That's perfect. Save to flash. And I go to the scope. And I look at velocity parameters. That looks more realistic. And autonomy, hallelujah. Okay, so we'll make a little single turn move here. And I'm going to go slow. So a little bit of encoder noise. I can hear it. The PP gain's a little high. I got a little bit of ring and overshoot there, so I'm going to turn the PP down. So you can see before the move, there's some quantization going on. It's a little bit less now that I turned the PP down, but still plus or minus 5 counts. And then after the move, it slides into final position. Maybe use a little bit more integrate. Depends on how much your load is going to be. If you got a large mass, this number comes down. 10-to-1 gear ratio, this would be, 10-to-1 inertia mismatch, this would be 100. And maybe you don't need so much integral, or maybe you do. Let's try a bunch of integral here. Too much integral, you'll get some overshoot on it. Oh, that looks pretty good. Kind of slides in. With a large inertia, you can't crank up the integral this much. Yeah, so there's too much integral, I get integral wind up. And so we'll come down about, I like to double things and cut things in half here, so. Still a little bit too much, so we'll say 400.